This lesson involves combinatorial proof, which is really fun. But before we begin, let's go back to something from the very beginning, which was sets and power sets. If you have a set A with n elements, why does the power set have 2 to the n elements? Now, this is something that we mentioned maybe even the first day of the semester. Okay, well, the answer, multiplication rule, of course, but let's really think why. Now that we have these counting techniques that we've been discussing, let's just go back and think about why. So let's say A is A1, A2, A3, out to AN. And now I want a subset of A. Well, I can make a subset of A by making a list. Of length n. Now, you might think, wait, subsets have no order, and lists of length n have order, but the list does not consist of the elements of A. So let's make a list. What I will do is go one by one. I have them labeled A1 through AN, and I will go one by one. And for each element, I will just decide yes or no. So the possible things is a list of length n using y and n. Yes and no. So, well, there are 2 choices here. Yes or no. And if I say yes, then I put A1 in the subset. And if I say no, then I do not. And there are 2 choices here. If I say yes, I put A2 in the subset. If I say no, then I do not. We have 2 choices here. These are the number of possibilities, 2 choices, etc., down to 2 choices. And you see the total number of which is 2 to the n. For example, the list with n no's, that's the empty set. And the list with n yeses is the entire set A. And this is really where this formula comes from. We can think about this cardinality by counting this list of length n over the 2 elements y and n, capital N for no. Now, let's get into some combinatorial proofs. Here is our first. Well, first of all, we have proved this. We used binomial theorem in the very last lesson. But I want to prove this another way, and that's involving a combinatorial proof. What is a combinatorial proof? Okay, well, what you need to do in a combinatorial proof is have a counting question and then show that the left-hand side of an identity and the right-hand side of an identity both count, well, they're both answers to the question, so they both count the same thing. If you have 2 expressions, they count the same thing, then they must be equal. And this is how a combinatorial proof goes. And the hardest part is usually coming up with what is the counting question, but we will practice some today. So hopefully, based on this warm-up that we did, if I talked about why is the power set, or why does the power set have cardinality 2 to the n when A has cardinality n, you can start thinking immediately about a story that both the left and the right-hand sides will count, and that is the number of subsets. Let A be a set with n elements. Then 2 to the n is the number of subsets of A. We need to show that the right-hand side also counts the number of subsets of A. So here we go. We can also count subsets of A as follows. There are n to 0 subsets of A with cardinality 0. Then there are, and choose 1, subsets of A with cardinality 1. There are, and choose 2 subsets of A with cardinality 2. And then this would continue. And the very last one would be when k equals n, right? Because this is a sum, k equals 0 to n. Here's k equals 0, k equals 1, k equals 2. And the very last one is k equals n. Maybe I will just put some dots and write that. There are, and choose n, subsets of A with cardinality n. And so, well, this is really the addition rule. There is no subset that has both at the same time cardinality 1 and cardinality 2. So these are they're all separate. We haven't overcounted anything. So we can just add all together. We have this many subsets of A. And, well, I will, just so I complete this, thus 2 to the n is this sum, k equals 0 to n of, and choose k. And now I was able to fit that, but I actually have my final statement that I would normally put, even with being low on board space. So this is a combinatorial proof. Now, let's prove another identity. This is Pascal's identity that I wrote on the board last time. And if you remember, this identity, together with the fact that n choose 0 and n choose n are both 1, is what makes Pascal's triangle really the binomial coefficients, or makes the entries the binomial coefficients. So let's prove this giving a combinatorial proof. Now, this means we do not use the formula for n choose k. And one of the reasons that I didn't give you the formula until the very end of last lesson is because I really want you to think about this as counting subsets. And this is important in our combinatorial proof. So what's the strategy here? Well, we need to think of a counting question that both the left and the right hand sides answer. Now, when I see a single binomial coefficient on one side of a combinatorial identity, immediately I think I'm counting subsets, because I know n plus 1 choose k is the number of k element subsets of a set with n plus 1 elements. So this is why this is a good strategy for you too. If you see a single binomial coefficient, think subsets somehow. I'm going to start with a set with n elements. And let's let B be anything that is not in A. Okay, we define capital B to be A union B. Now the first thing to observe, the cardinality of B is n plus 1, and this quantity, n plus 1 choose k, is the number of k element subsets of B. Now, we want to realize that the left-hand side also counts the number of k element subsets of B. So let me draw a Venn diagram here, and this will help us. Here is A, A has n elements. And then I have this one point out here, which is little b. And this capital B is A together with little b. Okay, well, now let's get to counting. Subsets of B with cardinality K come in two types. Well, either little b is in the subset or not. So I will say this type or this type. These are the two possibilities. Now, let's count these. So maybe I'll count the bottom one first. It is slightly easier. What do we see here? B is not in X. X is a subset of B with cardinality K. Now, come over to the Venn diagram. This means if you were in this bottom one, that X fully sits inside A, right? In this second case, because B is not an X. So then, in this case, X is a subset of A, and the cardinality of X is K. And we know how many are in this type. There are, and choose K of this type, because we're just counting the K element subsets of A here. Now this one, this is the other possibility, is that B is in the set X, this little b. And then, well, if we think again with our Venn diagram, if you take A, intersect X, okay, this will have one less element because, well, X has K elements and B is one of them. So X intersect A has one fewer element, which will be K minus 1 elements. So then X intersect A, certainly this is a subset of A, and this has cardinality K minus 1. And there are, again, A has n elements. Each X like this corresponds to one of these. So there are n, choose K minus 1 of this type. And this is the only possibilities. And there are no sort of things common to both. There are no subsets of capital B that are in both, because either little b is in X or little b is not in X. And there's no overlap here. So addition rule, we can just add. Altogether, we have n choose K minus 1 plus n choose K element subsets of capital B. And this proves what we want to prove. Again, I will put it here. So thus, we see that this n plus 1 choose K equals n minus 1 choose K plus n choose K. This is Pascal's identity. And this is a wonderful example of a combinatorial proof. You notice the entire proof. Never did I use this formula for n choose K, and you shouldn't in a combinatorial proof. You want to use a counting argument. Find a problem that both the left and the right hand sides count, and then they must be equal. Here's another combinatorial identity. We see a single binomial coefficient on one side, and so let's count subsets. We will. This time I'm going to let A and B be two sets. and I will make them disjoint with cardinality of A is M and cardinality of B is N. Now if you have disjoint subsets, that means that A intersect B is the empty set. Well then, this M plus N choose R, this is the number of R element subsets of A union B. Because A and B are disjoint, the cardinality of the union is cardinality of A plus cardinality of B, which would be M plus N. Okay, so now we know a story, and we have justified the left-hand side. We can create a R element subset of A union B in the following ways. Well, one possibility is we choose all R elements from A. And 0 elements from B. Another possibility is we choose R minus 1 elements from A. And 1 element from B. And this will continue. The next one, which I won't write, we would choose R minus 2 elements from A and 2 elements from B. But let me just put some dots, and I will get to the last one. We would choose 0 elements from A and all R elements from B. And this would be all different ways we can create a R element subset of the union. Well, now let's just count. Let's count, and we will add. Well, if we choose R elements from A has M things. That would be M choose R, and then choose 0 elements from B, and choose 0. Multiplication rule. Okay, choose R minus 1 elements from A, and then choose 1 element from B. So we have this many subsets. And then here, in the second one, we have this many subsets. Okay, and this would continue until the very end. We would have M choose 0 times N choose R of this type. M choose 0 times N choose R, many subsets. Thus, well, I will just make my final conclusion here. We have M choose R minus K, this sum, which adds up all of this addition rule. This would be the total number of R element subsets of A union B. And this will equal here. This is what we have proved. Okay, combinatorial proof. This is my last combinatorial proof in this video, and the first thing you should realize is there are no binomial coefficients here, so we are not counting subsets. If we look at the left-hand side, we see n cubed. We also see pn3, we see pn2. We should be thinking there's order in this problem, without a doubt. Okay, well, let's start maybe with the left-hand side. If we think multiplication rule, this is really giving us lists of length 3 where we have n possible elements to put in the list. So let me do this. Let A be the set 1 to n. And then n cubed is the number of length 3 lists using elements in A. Now we have the left-hand side. We need to argue why the right-hand side also counts length 3 lists with elements in A. There are, well, what's the first one we see? P and 3. This is the number of lists of length 3 with elements in A and no repetition. So there are P and 3 lists What else do we have? Well, let's think of a list of length 3. 1, 2, 3. And we have elements from A. Well, another possibility is we have one element that appears twice in the list and then a second element that's distinct. So there are, and I'll leave a blank, lists of length 3 with one element of A appearing twice and one element of A distinct. Now, before I even count that, let's think about all the possibilities. The final possibility is, well, we have no repetition. We have where we have one element appearing twice and one that's different. And the final possibility is that all three are the same. So there are, leave a blank, list of length 3 with one element of A appearing 3 times. And this would be all the possibilities. Let's count this one. We have one element appearing twice and one element that is distinct. Okay, here we go. First, pick the spot for the distinct element. There are 3 possible spots. Then I need an option for a distinct element, and I have n of them. And then I need an option for the repeated element, which I will put in the other 2 spots. Okay, now you notice, does this match? It looks a little different until you realize that n times n minus 1 is exactly p and 2. And maybe when I write the final line, I will mention that. But this is the number. And I will say it again, it was multiplication rule. First, I choose the spot for the distinct element. There are 3 of them. Then I pick the distinct element out of n, and now I need the one that will be repeated, and I can choose any of the n minus 1. And I will know exactly where to put them because I've already put this distinct element in its spot. So this is how many lists of length 3 with one element of A appearing twice and one element of A distinct. And finally, we have one element that appears 3 times. Well, just pick the element. There are n possible elements, and then you put it in all 3 spots. That one, I think, is perhaps the shortest one to count. Choose the element, put it in all 3 spots. Okay, so altogether, maybe I will even mention that as 3n n minus 1 is 3p Pn2, we have this, that n cubed equals Pn3 plus 3 Pn2 plus n. And again, just like the other examples in this video, when I added, it was the addition rule. All three of these options, there are no lists of length 3 that appear in more than one, because these have 3 different digits or elements from A, and these, there's 2 that agree and 1 that's different. And in this third case, they're all the same. So there's no overlap, and we can just add. Okay, and this is the end of this combinatorial proof.